Thank you so much for the invitation to come here to speak to Quasi-World. It's a great pleasure to be here at this time, and apart from the technical difficulties, I'm really looking forward to the talk. I can't hear you, so please do reply or ask your questions through the chat as we go along. So I'm going to be talking about the global dynamics of the pullback on multicurves for Thurston maps. This is something that Zachary talked about recently, and it's something that I've also been looking at for quite some time now with interest, but there's certainly plenty of room for improvement. I really like this subject because you get a wide variety of techniques that are coming in and being used, whether it be complex analysis or dynamics or group theory, symbolic dynamics. There's room for everybody in this subject. And so just a quick outline of what I'll be looking at today. I want to be looking at the pullback on curves. I'll define that. And then we are just going to briefly mention that you can understand this by looking at the boundary values of the pullback on Teichmuller space. This is something that Zachary was looking at in the last quasi-world, and so maybe I won't dwell on that so much, especially given that I started a bit late. So yeah, I guess last week or last month, Zachary was focusing on this side of things. So looking at the pullback on curves and the boundary of Teichmuller space. And I'll be focusing on this pullback on arcs in moduli space, because here the problem becomes a bit more susceptible to analytic and dynamical methods. And then I'm going to be looking at the virtual endomorphism on moduli space, because there we can use things like group theory. Sorry for that. So I guess both of my microphones are working now, but I'll stick with this one. Okay, so first the pullback on curves. We are going to be working with Thurston maps. These are branch covers from the two-sphere to itself that are postcritically finite. I'll maybe move through this material a bit more quickly because I think most of you all are familiar with this. And again, I'm a bit behind schedule. But a Thurston map is a postcritically finite orientation preserving branch cover from the two-sphere to itself. That is non-trivial. It has degree greater than or equal to 2. The basilica is a classic example of a Thurston map. We have a combinatorial equivalence on these branch covers. You should think of this as being conjugacy on the postcritical set. And then off of the postcritical set, you don't have a strict conjugacy, but you have a conjugacy in spirit where H0 and H1 are homotopic to each other relative to the postcritical set. So this is the usual definition.
Rocco, quick remark. I think one has to really assume isotopic here, because otherwise the homotopic could run actually through the postcritical points.
Okay, so when I said yes, I accept that correction. Thank you. Absolutely, we don't want that. Okay, so the reason we care about this equivalence is that it's exactly the right equivalence relation to put on branch covers so that you have a very nice rigidity statement. So Thurston's theorem gives a characterization of those Thurston maps that are equivalent to rational functions. You have the equivalence if and only if there are no obstructing multicurves. These are dynamically invariant up to homotopy multicurves. And perhaps I should be saying isotopy there as well. And the precise definition doesn't matter for us in this talk, other than to remind you that we care about the dynamics of multicurves under preimage of Thurston maps. And as I mentioned, this theorem is going to have a rigidity statement. So we are unique if realized as a Thurston map, assuming we have hyperbolic orbifold, and the uniqueness is up to Mobius conjugacy. So the proof of this theorem is something that is accomplished by understanding the pullback map on Teichmuller space. So the existence of the rational map that is equivalent to the Thurston map is given by studying this pullback map on Teichmuller space and identifying a fixed point for it. It turns out that the pullback map on Teichmuller space is weakly contracting. And so from this, you get uniqueness of the rational map quite easily. And so that's Thurston's theorem. But really, the thing that's always a bit alarming about Thurston's theorem is that we have to show the non-existence of certain obstructing multicurves, and a priori, assuming you have more than 3 postcritical points, so we're non-trivial here, you have infinitely many multicurves where you need to check that condition. And so Thurston's theorem is nice, but in practice, it can be quite hard to check that condition. And so really it's natural to try to understand what is happening to multicurves. And here I'm going to restrict our attention just to the case of 4 postcritical points, because come on, that case is hard enough as is. So there, the multicurves have a very particular form. They're going to be essential curves, and a essential curve in the sphere minus postcritical set is just a simple closed curve that separates the postcritical set into 2 pairs. And I want to consider these curves up to isotopy in the sphere minus the postcritical set. And so here's the main actor that we want to understand here. When you have 4 postcritical points, you can define this pullback function. You can define it when there are more postcritical points. It would be a pullback function on multicurves. But just for the sake of simplicity, I'm going to talk about essential curves up to homotopy. So the pullback function is defined on the set CF from before. And I'm going to add in this extra symbol, which means that the curve is trivial, meaning it's null homotopic or it surrounds a single puncture. And so mu f of a essential curve is given by gamma tilde, and where gamma tilde is an essential component of the preimage of gamma. You might worry about well-definedness here because perhaps you have multiple components of F inverse of gamma. But since we only have 4 postcritical points, all of those preimage components have to be homotopic to each other, or they have to be null homotopic, or they surround a puncture. Okay, so this is well-defined, and also we have to use the homotopy lifting property to argue for well-definedness here. But this is well-defined. And if there are no essential preimages, then we are going to say that mu f of gamma is trivial. So I really like this careful treatment given by Mario, Misha, and Anina on showing that the set of isotopy classes are in bijective correspondence with the rational slopes. And that is something that was definitely missing, at least in a clear way, in the literature. But what you can do now is, if you have a Thurston map, you can draw a picture of what this pullback on curves is doing, because as we said, every homotopy or isotopy class of essential curve has a slope attached to it. And you can plot the pairs P over Q and then mu f of P over Q, where I'm being a little sloppy with the notation. We said the rational numbers are in 1-to-1 correspondence with the curves. And so really you're understanding the pullback on curves to some extent by understanding this picture. So in this picture, I've shown this where the slopes are chosen to have absolute value of numerator and denominator less than 200. And the picture is quite complicated. And I believe with this example, if I drew more slopes, if I drew all of the slopes, the graph would be dense in R2. So it's a fairly complicated situation that we're looking at. And so you wouldn't expect the global dynamics to have any particularly nice properties, because we don't have continuity in this traditional sense, at least, of this slope function. And yet, it seems that if you ever have a postcritically finite rational map with hyperbolic orbifold, then the pullback on curves has very nice global dynamics. In fact, the conjecture is that it has a finite global attractor. That is, there's a finite subset of CF so that every curve gamma pulls back into that set or becomes trivial. And you'll notice that A is not unique, but you can always pass to a minimal such A if you want to have a unique global attractor that is finite. In general, again, I tend to focus on the case of 4 post-critical points because that's enough trouble as is. But you have the conjecture for more post-critical points as well. So let me just highlight some progress on this. So with the help of some software called NetMap, Bill Floyd and Walter Perry and others have been able to demonstrate that in many cases, you have many slopes that seem to be very well behaved. I'm not going to make it any more precise than that, other than to say, you know, if you look at 1,000 slopes, they tend to find a finite set very quickly when you are applying the pullback on curves. And so we've looked at dozens and dozens and dozens of examples, and they all seem to support the conjecture. What's interesting, and I don't know if everyone knows this, but you can actually look at our paper on origami and affine maps, and there you'll find a counterexample, or not a counterexample. You'll see that the converse is not true of the theorem. In particular, we give an example of an obstructed Thurston map that has a finite global attractor. I believe it's the obstruction. And so the converse is not true, and it's actually proven in the paper. I emphasize it up here. We're not actually proving things other than on finite sets of slopes, but we actually do give a proof of, or a disproof of the converse. There's been some exciting progress in recent years. So Misha has shown that critically fixed rational maps have finite global attractors. And even more so, he explicitly says what the global attractor is going to be. And then Mario, Misha, and Anina have studied the blown up 2x2 lattice maps and have shown that, again, when rational, they have finite global attractor. And then there's another result of Jem, Justin, and others for PCF polynomials. These have finite global attractors. And in every case here, maybe you could argue with me about this last case, but in most of these situations, you're using some nice combinatorics in the dynamical plane. Here with this last case, they're using some iteration on a combinatorial version of Teichmuller space. So there is something that is kind of a bit more Teichmuller theoretic going on, but for the first three, those tend to focus on combinatorics in the plane, talking about intersection numbers and things like that. So this is substantial progress that you see here, and yet you can see that the conjecture is wide open for non-polynomial maps with more postcritical points, or rational maps with 4 postcritical points that are outside of the cases that you've seen here. So we've got room for some more progress. And so I'm going to have us move along to talking about boundary values of the pullback on Teichmuller space. So I think I'll try to move a bit quicker in this section, unless there are complaints, so that I can get to some of the things that haven't been talked about more recently. So moduli space is the set of injections from the postcritical set into the Riemann sphere up to this equivalence relation. You're postcomposing by Mobius transformations. So this is a set of conformally distinct configurations of the postcritical set in the Riemann sphere. Teichmuller space is just the universal cover of moduli space. You can write it in terms of equivalence relations, and I do that here. So it's expressed in terms of homeomorphisms from the 2-sphere into the Riemann sphere, but it's really just the universal cover of moduli space. So they have the same dimension, and that is number of postcritical points minus 3. For us, we're going to be dealing with 4 postcritical points. And so the dimension is going to be one complex dimension. And in particular, for moduli space, it's going to be the Riemann sphere minus 3 points. As Zachary mentioned last time, you can just assume that 3 of these points are going to 0, 1, and infinity. And then the 4th point is going to be encoding the entire element of moduli space in the case that you have 4 postcritical points. So then we have the pullback map given a Thurston map and a point in Teichmuller space. Then the pullback of tau is tau tilde, where the following diagram commutes, and f tau is rational. These are purely topological objects in some sense. Their domain in every case is just the 2-sphere with no Riemann structure. And so the fact that you have a rational map here gives you some hope that you can actually do something with this thing using complex analytic tools. And so that is actually the case, that you can use that rational map that makes the diagram commute to understand what the pullback map is doing on the level of moduli space. So in general, Sarah has shown that there's an intermediate complex manifold, WF, and a covering map Y a holomorphic map X so that the following diagram commutes. Pi is the universal covering projection. Sigma F is the pullback map on Teichmuller space. So this is a general scenario. If you have any Thurston map, even an obstructed one, you have this diagram. And this gives us hope that we can actually understand the pullback map because we have some algebraic object down here. It's especially nice when X is injective. I'm not always going to be assuming that in this talk, but if X is injective, then you have, instead of, well, you still have the correspondence, of course, but you in particular have a map here. How much time do I have? When should I stop? I guess I should ask.
Well, I think you started at 15 after, right? So let's say 5 minutes after the full hour.
Okay, that's very generous. Thank you. All right. So yeah, in many situations, you have just a straight up map on moduli space. And I'll go through the computation just to show you what one of those looks like. You all maybe have seen the solution to the twisted rabbit problem that is given by Bartholdi and Nekrashevych. For the rabbit polynomial, the map on moduli space is 1 minus 1 over z squared. And so that's one example of a map on moduli space. Just to show that the rabbit isn't the only map, here's another quadratic Thurston map. There exists a quadratic Thurston map. It is rational, and it has this ramification portrait. Infinity and 0 are simple critical points, and they map in a 4 cycle in this way. And I'm just going to show you briefly how you would find the map on moduli space for this Thurston map. So what you would do is, I've written down the pullback diagram just to remind you. We're going to normalize tau and tau tilde in kind of a weird way, but it's certainly legal. I'm going to send 0, 1, and infinity to 0, 1, and infinity under tau tilde. And then the fourth point is going to point somewhere in moduli space. I've normalized so that this point is going wherever, and we'll call that X. Likewise, down here, I'm going to normalize 0, infinity, and the fourth postcritical point to go to infinity, 0, and 1. And then 1 I've normalized to go wherever it goes. So I guess I haven't normalized 1 is a better way of saying it. And so what you can do is just do some diagram chasing to see what the mapping properties of f tau are. So I'll do one really quick here. So 0 was mapped by the Thurston map to dot. And so tau tilde is going to take 0 to 0. Tau, we declared, takes dot to 1. And so f tau has to take 0 to 1. All right, so it's just a diagram chase. You can do that for all 4 of the postcritical points and see that you've produced f tau with this map, with these mapping properties. Well, f tau is a rational map. These are all degree 1 maps, except for this one, which is degree 2. So you know this is a quadratic map. And you have enough data here actually to figure out what the map is. G of x is 1 minus x squared, which is the basilica polynomial in slightly different coordinates from what I had before. Okay, so that's an example of a map on moduli space. And I just want to mention that these are all over the place. So examples with a map on moduli space abound. So there's kind of a nice argument that Greg and I gave that every map with, oh my, let's generalize here, less than or equal to 3 postcritical points is going to arise as a map on moduli space for some Thurston map. There's just a little game that you can play with fixed points and post-composing with Mobius transformations to show that every one of those arises as a map on moduli space. Also, maybe to convince you that this is a reasonable class of Thurston maps to look at. Greg and I classified all of the quadratic Thurston maps that are having hyperbolic orbifold. And every one of the, let me back off there, the ones with 4 postcritical points. So we classified quadratic Thurston maps with 4 postcritical points in hyperbolic orbifold, and every one of those had a map on moduli space. So you're looking at some of the ramification portraits here and the maps on moduli space. Here's more ramification portraits, and every one of those had a map on moduli space. So it might have seemed like a strict restriction at first to just look at those that have a map on moduli space, but there are a lot of them. And so I'm going to be giving a theorem in a little bit that does require us to have a map on moduli space. So that's the part where I'm looking at curves, sorry, that's the part where I'm looking at pullback on arcs. I will need a map on moduli space there, but when I talk about virtual endomorphisms, you can have any correspondence arising from a Thurston map with 4 postcritical points. So just briefly mention the Weil-Petersen metric. Zachary talked about this. Teichmüller space is not complete under the Weil-Petersen metric. But you can look at the Weil-Petersen completion. The action of the mapping class group extends to that completion, and also very significantly for us, Nikita showed that the pullback map extends to that completion. So it takes strata into strata where the stratum corresponding to gamma is going into the stratum corresponding to the pullback of the arc gamma under the Thurston map. And so this is really giving us the first commutative square in this diagram that I keep mentioning. So the first commutative square is coming from Nikita, because when you have 4 postcritical points, the strata are only consisting of a single point. They're more complicated if you had more postcritical points, but you actually have a bijective correspondence between curves and strata here, and the following diagram commutes. And if you choose your normalization on Teichmüller space correctly, then the Weil-Petersen boundary is just the rationals together with 1/0, which in hindsight is maybe not so surprising since there's a bijective correspondence with the curves which have slopes assigned to them. And so I'll mention that Zach was really using this Thurston pullback map on Teichmüller space to understand the pullback on curves. So I think that the previous results that I showed were in some sense discrete, right? You're not really using any kind of underlying geometry for where the curves are living. But when you consider them as the frontier of Teichmüller space, then you have some geometry coming into play. So that's exciting direction there, but I'm going to move along to talk about pullback on arcs in moduli space. And as I mentioned, this is where I'm going to be restricting to the case where we have a map on moduli space. The map on moduli space, well, remember, moduli space is just the Riemann sphere minus 3 points. And G is just a rational map when you extend over those 3 points, the removable singularities. The fixed point of the pullback map on ticular space is going to project to Z0 on moduli space. Okay, so we had the fixed point up here. That's going to project to a fixed point of this map on moduli space. And this map on moduli space, you can argue, just using basic mapping properties, it's not hard. You can argue that this is postcritically finite and that the postcritical set is contained in the set of the 3 points. All right, so P is a set of 3 points coming from our choice of normalization of moduli space. So I'm going to define an object here. L of Z0 is the set of arcs that are emanating from Z0. So L of 0 is Z0. L of 1 is going to be in the set of 3 points, and it doesn't intersect those 3 points in its interior. So L Z0 is a set of arcs emanating from Z0 and ending in P, and we consider these up to isotopy in the sphere minus P1. So natural enough, it's a companion definition to the curves, essential curves. So the pullback is maybe not exactly analogous. So Z0 is going to be a fixed point that is not critical. And the reason it's not critical is because the postcritical set, as we said, is not intersecting Z0. So we know that Z0 is not critical. And so you have a unique lift of arcs under G based at that fixed point Z0. And so what you can do is pull back your arc. So you have some point that's fixed, Z0, and then you have some arc lambda that's terminating in the postcritical set, and we're just going to pull that back under G. There's a unique lift that is going to be based at Z0, and if it doesn't terminate in P, so if this lift doesn't terminate in P, we are going to say that LG is trivial, the pullback on arcs is trivial. Otherwise, we take the lift if it does terminate in P. So just to be very concrete, let's look at the basilica. So here's the basilica. If you have the 1/3 ray here, then LG of the 1/3 ray is equal to 2/3, because when you look at this arc here, that maps under G to that arc in a 1-to-1 fashion.
So what is Z0 here?
Yes, thank you. Z0 is this point. So 1 minus the square root of 5/2. It's, yeah, thank you. That's very important. So what I've just shown you is that LG of 1/3 is equal to 2/3, and also LG of 2/3 is equal to 1/3, because G takes the 1/3 right here. But I'm being a bit selective in the way I've chosen my arc, right? I mean, I chose a very special arc when in general you should be thinking of, maybe something a bit more like this, right? So arcs can be quite complicated, but for the sake of an example, it's nice to have a simple example. I'm glad Mario pointed out that the fixed point matters, because we have another fixed point, 1 plus the square root of 5/2, and that has, for example, the 0/1 external ray, which is going to be invariant, and so you have this. So really the interesting question would be to compute LG of this purple arc and try to understand what's going on there. And so in fact, we can understand that quite well. So let me theorem here. So you have these special Bookshire rays. I shouldn't call them internal rays, but they're Bookshire rays that are connecting Z0 to the set P. And I just showed you a bunch of them for the basilica. They are clearly in this set of arcs up to homotopy that I'm considering. It's clearly going to be a finite set for topological reasons, because they can't intersect each other except at their endpoints. And it's going to be invariant under arc pullback. So that's nice, but what's really important here is that if you have a PCF rational map with repelling fixed point and an arc, then this is basically a finite global attractor for the pullback on arcs. You can pull this back to one of those internal rays or Bookshire rays, or you end up being trivial. And so that is giving us a finite global attractor for the pullback on arcs, which is great, because we're going to show that there's a correspondence between these arcs and the point in type and points in the Weil-Petersson boundary, or curves, essential curves for the Thurston map. So this is something. We're on our way to theorem here. The proof of the lemma, I don't know. Is this something I should prove? It's basically just using the expansion of G in the Poincare metric. You have to use the orbifold metric if G is not hyperbolic. But just when you're pulling things, when you're lifting things under a rational map, lifting arcs, they have certain limiting behavior. I guess I'll just mention quickly the various cases that you have, and not say a whole lot. If you have the arc terminating in a Julia point, so a point that is not in the Fatou set, then you have Z0, you have this point in the Julia set that is also in P, and under pullback, Z0 is repelling. This point is repelling, assuming you've passed to an iterate and made it a fixed point. So you have this arc being pulled in both directions, and by expansion, you know that eventually it has to break. It has to map to an arc that doesn't have an endpoint in P. So that's one case. The other case is if you're in a pre-periodic point, and that's probably the easiest of them all. And in the case where you are terminating in a point of P that's in the Fatou set, that's a bit tougher. You have to, I suppose there's various ways that you can argue here, but the idea is that in the Fatou component, your dynamics are conjugate to the power map, and then everything outside of the Fatou component has diameter shrinking to 0 as you're lifting, and so from there you can argue that that is converging in the Hausdorff metric actually to a internal ray. Okay, so That's a nice result on the pullback on arcs. And I forgot the most important thing, which is the theorem. Here is a global attractor result for the pullback on curves now. All right. So before we were thinking about maps on moduli space, but if you have a rational map with 4 postcritical points and a map on moduli space, then the pullback on curves has a finite global attractor, and the elements of that finite global attractor, if you take the minimal one, is going to be in bijective correspondence with the internal rays emanating from Z0. Okay, so this is relating a dynamical property of the map on moduli space to the global attractor for the map. And what is the connection? Well, if you have a point in the boundary of Teichmuller space, you can connect it to the fixed point of the pullback map, and that is going to push down to a arc in moduli space based at the fixed point of the G map that is going to end somewhere in the set P. And when you apply sigma F to this arc, that is, by the commutative diagram produced by Sarah, going to be the same as lifting this arc under G. So it's actually a pretty nice correspondence here between points in Teichmuller space and arcs in moduli space. So that's the first, yeah.
But Russell, a quick question. You know, these points in P in moduli space, I mean, they have infinitely many pre-images in Teichmuller space. So how do you get then a finite set A?
Okay, so yes, good question. So every one of these arcs pushes down to an element of what I was calling lambda Z naught in moduli space. And what I had said on that previous theorem was that the dynamics of LG on lambda Z naught is going to have a finite global attractor. So under iteration, you get a finite global attractor for this pullback on arcs. And so that gives us, let me be consistent with my notation. So A is here. And so I have a finite collection of arcs here, RZ naught. And the theorem using the Poincare metric and expansion was arguing that every one of these rays is going to land in this finite global attractor. And so every arc connecting the fixed point to the boundary is going to iterate to essentially a lift of one of these internal rays to Teichmuller space. And it's the lift that is going from the fixed point to the boundary.
Yeah, I got it. Okay.
Okay. So really we're using analytic tools on moduli space to conclude something about the global attractor. And that's kind of exciting, right? Because we like studying dynamics of things on moduli space. The real question is, what if we have a correspondence instead of a map on moduli space? Is there some dynamically meaningful object associated to that correspondence that is going to be corresponding to global attractor? And that seems to be not a trivial question, but it's a very interesting one, and it hasn't been thought about too much. Okay, so the last thing I want to mention is that we've really highlighted some various tools here. So Zach is essentially looking at mapping properties. Other folks have looked at intersection numbers, essentially on the dynamical plane. Here I showed you how to use some analytic properties of the map on moduli space. And of course, very briefly, I'm going to introduce you to some group theory methods that you can use to understand the global attractor question. And it's been used successfully in quite a few cases. Sadly, some of those have been subsumed by new results that people have done, but still, this is actually, I think, a very viable approach to the finite global attractor question. Okay, so I'm going to be studying the virtual endomorphism of the correspondence on moduli space. Virtual endomorphism is a map from a finite index subgroup into the group. When we have 4 postcritical points, there's that restriction. Then we have that the fundamental group of moduli space is the free group on 2 generators. And so I'm going to associate a meaningful virtual endomorphism to a correspondence on moduli space as follows. The finite index subgroup is going to be the set of liftables. So this is a set of elements in pi1 that lift to a loop gamma tilde under y at your preferred base point. So it's actually not z naught, but it's the push down of the fixed point on teichmuller space. Small detail. But the virtual endomorphism I'm going to define is you take the lift gamma tilde and then apply x. So that was the map on the right in the correspondence. So you have a base point here, you have a loop. It lifts to a loop up here at the base point, and then that's getting pushed down under x, which is a continuous map to a loop on moduli space down here. All right, so I've defined the virtual endomorphism associated to this correspondence. And given that I have 1 minute left, let me just say briefly that you can encode the points in the Weil-Petersson boundary in terms of these so-called parabolic elements of the fundamental group on moduli space. So they have a very special form. If you think of these as elements of the fundamental group, right, they're in the deck group of the universal cover. And so they're stabilizing a point in the Weil-Petersson boundary. And it turns out that it's not a deep fact, but that if you look at this virtual endomorphism on this restriction to these so-called parabolic elements, then you are doing the same thing as looking at the pullback on curves, sigma f on the Weil-Petersson boundary, and this pullback on the arcs. And so I'll just mention that if you have an arc emanating from Z naught, how do you produce a parabolic guy? Well, you do what Laurent calls the lollipop associated to this arc. So instead of taking the arc, you produce a loop by following along, going around a small loop around the point in P, and then coming back along that arc. So that's produced a loop associated to the arc. And so once I've done that, it's actually not so unbelievable that this diagram is commuting, because you're just lifting arcs or lifting loops, and they're very closely related. Okay, so let me just state the theorem. So Kevin used this to get a finite global attractor for quadratic polynomials. That's been superseded by the other result that you saw. I was able to prove finite global attractor for this function. And again, I think there are other ways of proving this, but it seems like this algebraic method is really working for any map with 4 postcritical points, not just the ones that have a map on moduli space. So I just wanted to bring that to your attention, and thank you all for your patience. Thank you for the liberty of having some extra time here.
Yeah, thanks a lot, Russell. So let's thank the speaker.
All right.
So let me open the discussion. So comments or questions?
Yeah, maybe one comment rather than a question. Yeah, so like I think like one of the powers of this algebraic method is that it not only like allows to, it does not only allow to solve the global curve attractor problem, but also to look at the Thurston problems as well. Yeah, and that's
that's a very good point. So the group theory there was inspired by Bartholdi and Nekrashevych's work, and they're somewhat different problems when you get on the ground, but from 10,000 feet, it's really just understanding this virtual endomorphism. So yeah, thank you for that. It's a good comment.
Other comments or questions? Well, what are the future directions?
Yeah, you know, I'm like I said, I'm really excited to try to understand the dynamics of correspondences and see if we can find something. I've had a student who's just drawing pictures of orbits of points under these correspondences. It's not even so clear what the orbit of a point means in that context, because you have multiple pre-images. And so, yeah, I've drawn some pictures. I haven't come up with anything conclusive there. But then, yeah, the other direction I think is to try to make this algebra work for us to prove finite global attractor, because I think, I mean, so like I said, people have been using dynamical plane combinatorics to understand the pullback on curves. But if you have a Sierpinski carpet Julia set, the combinatorics might be there, but I think they might not be the right kind of combinatorics to do what we want. And so I see this as being, in my opinion, the best way of attacking this question for post-critical questions, but I would love it if someone proved me wrong.
So other comments, questions? Well, let's thank Russell again, and let me stop the recording.